Assimilation, or JCSDA. So if we get Travis's slides up, get us started.
Coherent, that's why. So thank you. So yes, I'm Travis Sluka. I'm the SOCA project lead at JCSDA. SOCA is standing for the Sea Ice Ocean Coupled Assimilation. We actually do a little bit more than that these days, but just think of it as the Marine DA with JEDI. You should hopefully know who JCSDA is by now, but just as a recap, so partner agency between NOAA, NASA, Navy, Air Force. For the Marine side, we work primarily with the needs of NOAA, NASA, and a little bit of collaboration with the Met Office through the Air Force. Surprisingly, not the Navy. Hopefully, someday that'll change. So what it is that we do. So in terms of Ocean DA capabilities, SOCA has kind of three main priorities. Those being, we're not responsible for operation, for putting systems in implementation. That's, for the NOAA side, that'll be EMC. But our aim is to provide a suite, basically a menu of DA options that are available, tested, demonstrated for easy implementation at NOAA and NASA and the community as well, focusing on the UFS marine components. We aim to consolidate DA efforts. The ocean DA community is quite small, and what few people we have are seemingly pulled in different directions. So any collaboration we can have within the ocean DA community and with the non-ocean people is very beneficial. And I'll show some of the benefits of what we get by leveraging the JEDI framework. We basically get to steal from the atmosphere and make it work in the ocean, which is a huge benefit. It makes my team a lot smaller. And we hope to accelerate marine R2O and innovation. So one of the nice things that I'll have some slides about are that one of the big things we plan to work on is coupled data assimilation. So by having all of your UFS DA components within JEDI, it should make things very easy to start doing work in terms of weakly coupled and strongly coupled data assimilation. This is going to be a focus topic for us next year and going forward. So the components of SOCA, we have the ocean, MOM6, sea ice, SI6. We have biogeochemistry. I know not really part of UFS, but it is a module you can compile within MOM6. And then we have the air-sea interactions between all of those components. We also have waves, however, noted there, we have insufficient resources to really do anything with that, so if there's any volunteers, please talk to me. We would love to start doing more in terms of wave DA in the near future. So the targets for SOCA, NOAA, and NASA, we are developing the software for the quarter degree and ocean ice initialization globally. That's already been used at NOAA for developing the 40-year NG GODAS reanalysis, and that is available for free on AWS. And we are working with NOAA on the implementations for the GFS 17, GEFS 13, the target for that being a considerably more advanced hybrid LETKF ENVAR, and also working with NASA on their upcoming quarter degree system. We're also doing work on regional DA. Right now we're doing a lot of experiments with the HAT 10 domain, working our way up to 1/12th degree. And this will have immediate implications for HAFS DA in the coming year. So like I said, one of our top goals is to develop a menu of DA options. And so ocean DA traditionally has lagged behind the atmosphere. A lot more resources are poured into atmospheric DA compared to the ocean. So the most advanced ocean DA you would typically see operationally would be a 3D VAR at the top there. But by stealing what they use in the atmosphere through JEDI, we basically now have a functioning 3D VAR FGAT, LETKF, hybrid LETKF ENVAR, and a hybrid EDA ENVAR. And those we have all demonstrated to be working reasonably well. Obviously, before you put something into operations, you do quite a bit more tuning and testing in your own end. But the framework for these is ready to go within JEDI. This year, we're going to kind of wrap up our suite of methods here with the 40 method, so 40 LETKF, 40 ENVAR, and have this all available within Skylab and being demonstrated on a regular basis with the marine components of the UFS model. In terms of more innovation in the coming years, we will be working on a 40 VAR, coupled DA, and any future methods that JEDI has available that we haven't played around with yet. So I know there is a group working on particle filters. So having particle filters available within JEDI will make it easy to use for any of the ocean components. So what is JEDI and why does it help Ocean DA? So if you look at this chart, the blue stuff is all the common JEDI components that we use, and the red are the model interfaces. So I am that top red box. I am SOCA. So I care about interactions with MOM6 and SCI6. And I can use these components in JEDI, kind of a mix and match, use what I want to implement my DA system. So in terms of the data assimilation algorithms, your B matrix, how you handle observations, variable transforms, all these things, that's all common components. They are handled by the JEDI team and is outside of my concern. It's something I don't have to maintain. So by doing this, JEDI is a model agnostic toolkit. So this considerably accelerates the DA development that we have on the ocean side. As an example, so if you look at this, this is our horizontal correlations that we use within the ocean. So typically, a lot of times what you do in the ocean would be, in what is used at the Met Office, is a diffusion operator to model your correlations and have them spread out along the coastline correctly. Such a thing is hard to implement correctly and have it work. So there's no way I would want to do that. But we can use these common components in JEDI, one of those being SABRE, to do this static B modeling. And this is basically no coding on my part. I just use these already available parts of JEDI. Similar thing for how we handle observations. So in terms of quality control and forward operators, those are all available within JEDI, and a lot of those can be configured just with code. Just with configuration files, no coding on my part. So that's kind of an overview of what SOCA is being built on top of JEDI. So the current status of adoption at NOAA, I've got a couple slides here. And I know this slide has been showed a couple times because this is actually very impressive progress that we have. So EMC is using SOCA for, like I said, the upcoming GFS 17, GEFS 13, and the target for that being an ensemble-based hybrid LETKF ENVAR. And so they've started doing some experiments with that. You can see that chart there. The red line there is the current SST from GFS being produced with NSST. The red line is kind of our ocean-only analysis. The one below that is the coupled UFS, but using the SOCA 3D VAR, and then the line even below that is closer to what the target is of using an ENVAR, but with a static ensemble. The hope would be with the full dynamic ensemble would be another line even below that, but we'll see that when it happens. So this is actually very encouraging that the ocean DA is very mature right now with the prototype for GFS 17, GEFS 13. So I know a lot of people are sleeping a little bit better at night knowing that SOCA is actually working quite well with the ocean side. Still some work to do probably on the ice side, but at least ocean is working quite well. And this has been shown as well also by other people how even looking at radiances from, in this case, AVHR channel 3, once you put SOCA in there, that bottom plot, your O minus B's for your radiances are a lot better. We are getting a considerably improved ocean state. So that's all very encouraging. Also, CPC running some experiments with version 8 of UFS and for ENSO hindcasts. So if you look at the, in this case, 6, 7, and 8 month lead times, the system of the UFS initialized with what is SOCA here, they call it Glory, that the correlations are quite a bit better. How much of that is the model, how much of that's the initial conditions, that would have to be torn apart. But as the DA person, I would like to take credit for the initialization probably. So it does bode well that the experiments both at CPC and EMC are showing that the ocean DA is performing quite well already. Thinking more towards the future. So like I said, having everything within a coupled framework lets us to do something that's been sought after for a long time in the DA community, coupled DA mainly, and strongly coupled DA. So if you look at all these components of the UFS that I care about, I think it's basically land and chemistry that have been left out. But anything that touches the atmosphere that's marine, any of those lines there are a coupling that we could possibly get useful information out of. So we have a relatively mature ocean DA system, sea ice system. Someday, hopefully, we'll be dealing with waves and biogeochemistry a lot more. And that gives you a lot of lines there in between of coupling between these components that you can get useful information. So right now we already have strong coupling between the ocean and the ice. The sea ice concentration, the SST are tightly coupled when you do your data assimilation. And the hope would be, once we have this all within one system, you can start looking at these interactions between all these components and start to get useful things from it. So we'll have the framework for that in place within JCSDA by the end of this year. And so the goal for later on this year and next year is to really look at two main things. So using the CRTM to do surface sensitive radiance data assimilation with AVHR and GMI, so looking at SSTs. So within one DA system, can we use these observations to update the ocean and the atmosphere at the same time in a way that is beneficial to both domains? And another fun project using NASA's OASIM model. So we have an ocean color forward operator, and so we will be assimilating the visible channels to impact ocean biogeochemistry, and doing this within a coupled framework. What can this tell us about the other domains? And I know it was mentioned, wave DA, most people don't care about wave DA because it's such a strongly forced system. And that might be true, but within a coupled context here, what fun things can we do with it? Like if you have wave observations, what does that tell me about, atmospheric winds or upper ocean conditions? And a lot of these fun scientific questions I think we'll start answering in the next year or two once we have this coupled system up and running. And with that, I will take any questions.
Trying to. We have two majors.
I mean, Travis, we and I have been talking, but in this presentation, I want to bring it up again. In this presentation, I don't see any TNS profile assimilation. So, what is your plan for TNS assimilation?
Yes.
Temperature salinity
Yeah,
in
yeah.
situ ops.
Yeah. So these initial experiments we've been running, we've been focusing mainly on satellite SST and altimetry because they're the most plentiful. We're doing some work right now with updating the QC filters for temperature and salinity for in situ observations. And so in our next round of experiments, those will be thrown in probably 2 months from now. So I think next quarter we should start a next round of experiments with a more realistic full set of observations of what you would use operationally, and we should have some results to show for that.
Time for one quick question.
Hi, Travis. You showed very encouraging results from the weekly coupled DA that's going to be implemented in GAPS version 17. Have you looked at how the system, how the data assimilation scheme works with the pre-argo period? Does that perform equally well when the data is sparse in the pre-argo period?
Well, we do have the NG GODAS. That was a 40-year reanalysis. I haven't looked at those results too much. That was just with a very basic 3D VAR. I think it is something we want to look at with our experiments, sensitivity to observations when you do have sparse in situ. And so we'll probably be looking at that in greater detail with basically how the different DA methods behave when you have different, observation coverages. So I think by the end of this year, hopefully we can show some of that.
All right, well, let's thank Travis one more time. All right, thanks, Travis. So next up, we've got Christopher Cox from NOAA PSL.